The rest of today's lecture has to do with thermodynamics. With thermodynamics, right, we're talking about energy. We're talking about energy, which is the ability to do work. And in this case, we're going to look at energy with respect to transferring heat. You're familiar with a few different types of energy, right? You're probably familiar with kinetic energy, which is the energy of motion, potential energy, the energy relative to your position in a field. We're going to be talking about internal energy based on molecular composition, and we're also going to be talking about heat, which is kind of related to the temperature. We have kinetic energy, which is the energy of motion, right? And that's based on your mass and velocity, right? So kinetic energy equals 1/2 mass times velocity squared. I'm not going to give you a question like this in chemistry, but this is like a classic physics example of what's the kinetic energy of a 1,200-pound car traveling 50 kilometers an hour. But it's good to just remind ourselves of the definitions, the different types of energy. So just a brief review on some of the other forms of energy, right? Potential energy, energy relative to your position in a field, like gravity. So if I took a book and picked it up off the ground and held it 6 feet over the ground, the potential energy of that book would be because it was 6 feet off the ground and gravity would pull it to the ground if I let go. The same could be true for the water that's held behind this dam, right? We're talking about the elevation of the water at the top of the dam relative to the bottom of the dam. So we can calculate potential energy, right? That's going to equal the mass that we have multiplied by the gravitational constant times the height difference that we're talking about between the two positions. The energy we'll be talking about in this class will have to do with chemical energy, and we can kind of think of it by looking at this example of a sodium ion and a chloride ion and the relative distance that they are apart. And so those two oppositely charged ions, the farther apart those ions become, the less potential energy we have, the less attraction we have between those oppositely charged ions. So think of two different magnets. When they're really close together, right, there's a strong potential energy pulling those two magnets together. The same thing can be said here for the sodium and the chloride. The farther we pull them apart, there's less and less potential energy of attraction between those two. And at the same time, if I push them too close together, now there's going to be a repulsion because they can't go that close together. Now we're going to start having repulsion between the positively charged nuclei in both of those atoms. We're also going to think about how we can convert energy, right? So the cyclists at the top of the hill here, they have high potential energy because your energy is relative to your position in the field. They're high on top of the hill, but they're not moving. They have a low kinetic energy. Well, they're able to, as they move down the hill, they're going to get a decrease in potential energy because they're getting closer and closer to the bottom of the hill. At the same time, you're getting an increase in kinetic energy. So we're going to look at how we convert energy, right, from one form to another. And that was put forth by Hess. And that's the first law of thermodynamics, that we need to have our total energy, right, must remain constant. So in that cyclist example, they are taking their potential energy, their energy relative to a field, and they're converting it into kinetic energy. So that's very important, right? Energy can be transformed to one form or to another. I can take potential energy and convert it into kinetic energy. And when Hess was working on this, he was thinking about engines, but this applies in chemical reactions as well. The total energy we have must remain constant. When we're talking about the chemical energy, we need to talk about where it's coming from, where it's going to, and so we need to define two different things. The system is where our reaction is taking place, right? So in this piston example where I may have a combustion reaction, this would be my system. This is where my reaction is occurring, and so maybe the energy is going from my system to the surroundings, or maybe it's going from the surroundings to the system, but the system is where the reaction is occurring, and the surroundings would be the piston in this case, everything that surrounds the reaction. we're going to be interested in tracking the total change in energy during the course of the reaction. And when we're looking at that internal energy, that's the sum of kinetic and potential energy. Right, and that's what we're interested in. We are interested in tracking the change in internal energy between the start and end of a reaction. Or we can find that total change in energy by basically looking at where do I end in energy and where did I start in the energy, and what's the difference between those two to get the change in energy during the course of that reaction. And of two types of reactions, we're going to have reactions where the final energy ends up at a lower energy, and we're going to look at a reaction where final energy ends up at a higher energy in the course of the system. So as you'd imagine, in this case, right, the change in energy is less than zero because I've lost energy during the course of that reaction. So that this reaction has released energy to the surroundings. And we're also going to look at reactions that end up at a higher energy where my change in energy would be greater than zero because I've gained energy during the course of that reaction from the surroundings. We're going to look at two ways of changing the internal energy, and one is through heat, right? We are all familiar with heat. Heat will flow from an area of high internal heat to an area of low heat, right? Things that are warm will radiate heat to things that are cooler until they reach a thermal equilibrium. So our heat will flow from an area of high heat to low until a thermal equilibrium is met. We're going to look at two different types. Here is my system. It's this lockbox. I'm going to look at heat that can be lost and heat that can be gained. So if my reaction loses heat, right, from the system to the surroundings, I'm giving off heat. That would be a negative Q. So heat is lost from your reaction, right, from the system to the surroundings. Whereas our positive Q, that system must be gaining heat from the surroundings. Heat is gained by the system from the surroundings. So here's our example of heat lost, right? The reaction is losing heat to the surroundings. It's giving heat away. And here's our example of heat gain, where I'm putting heat into the system. I'm going to see an increase in internal energy, whereas heat lost will result in a decrease in internal energy. We're going to look at this heat of reaction with respect to during a chemical reaction. Does that chemical reaction release energy to the surroundings, or does that chemical reaction absorb energy from the surroundings? The other component of energy transfer is work. We can transfer energy through heat. We can transfer energy through work, right? Work is the ability to move something. So if we have a negative work, right, again, we are losing energy to the surroundings. We're losing that energy to the surroundings through doing work on the surroundings. So the system, from the system. the system performs work on the surroundings. So thinking of this, it's hard to think about in the case of the safe, but if we were to think about it in terms of that piston that we saw earlier. Here's our piston. This would look like, well, in our reaction expands and pushes that piston up. That would be a negative W because our system expands, it's doing work on the surroundings. So a reaction expands the piston, right? It pushes that piston up at the expense of energy. The opposite would be a positive W. Now the surroundings are doing work on the system. So that would be the opposite. That would be the compression, right? The piston being pushed down, compressing the system. The importance of defining heat and work is that that's how we're going to track our change in energy. Our total change in energy will equal what was the heat gained or lost and what was the work energy performed or absorbed from that system and the surroundings. So in summary, for heat, right, heat gained, that would be a positive Q, the system gains heat. For a negative Q, that means our system is going to lose heat, and the same can be said for work. Positive work means work is done on the system, I'm absorbing work energy. A negative W would mean that my system is performing work on the surroundings. And so let's just look at a simple question from the homework that would go over a sample calculation like this. So question 5.15. The air in an inflated balloon, which would be our system in this case, absorbs 125 joules of heat. As it absorbs that heat, it does 85 kilojoules of work against the surroundings. What's the change in internal energy in kilojoules? So our Q, we absorb, right, a positive 125 joules. Our work, we perform, right, 85 kilojoules worth of work. We lose 85 kilojoules worth of work. And they want to know what's the total change in energy, where total change in energy equals Q plus W. Well, the one trick to this calculation is they were tricky and they gave us the heat energy in joules. We need to convert that to kilojoules. And we know that for every 1,000 joules, we have 1 kilojoule. So I divide that by 1,000 to get 0.125 kilojoules. Now I can do my calculation. Now I could find that the change in energy equals a positive 1.25 kilojoules minus 85 kilojoules of work energy to see that the total change in energy during the course of would be a negative 84.875 kilojoules. And reporting that to the final correct significant figures, I've got two significant figures here, so we'd actually round that answer back up to about negative 85 kilojoules to two significant figures. So as you can see, the heat absorbed had a very little impact on the total change in energy because we did so much work during the course of that reaction. We're going to look at two types of reactions and their heat transfer. The first are exothermic reactions. You're familiar with them because an example of an exothermic reaction would be a combustion reaction, right? Burning wood in your fireplace or your stove. Another example would be those hand warmers, right? A cold winter day, you take those hand warmers and you put them in your gloves and they warm up your hands because they're an exothermic reaction. They are releasing heat to the surroundings. Reaction or process that releases heat to the surroundings. And so that would correspond to a negative Q, right? We're losing heat to the surroundings. What it looks like with a reaction coordinate diagram. So here's the energy of my reactants. Here's my energy as a reactant. I need to go up and over the activation barrier of the reaction to get the reaction going. But once the reaction forms products, I'm releasing energy during the course of that reaction in the form of heat. That would be an exothermic reaction, a loss of heat during the course of that reaction. We also know of endothermic reactions. So endothermic reactions are the exact opposite. They are going to absorb heat during the course of that reaction. Reaction or process that absorbs energy from the surroundings. So previously in the exothermic case, we were releasing energy to the surroundings. In the endothermic case, we're absorbing energy from the surroundings. We're going to end up at a higher energy than when we started. Higher energy the reaction started. An example of an endothermic reaction, right? Those instant ice packs. When you break them and the two chemicals mix, the ice pack gets cold. The ice pack gets cold because it's endothermic. It's absorbing all of the heat energy from your forehead or from your ankle, and that's why it feels cold. It's absorbing that energy. And so as a result, here's the energy that we're starting at for our reactants. We're going to absorb energy during the course of that reaction, and we're going to end up at a higher energy with our products in an endothermic reaction. And the sign for that, right, would be a positive Q because we're ending at a higher energy, so I must have absorbed energy during the course of that reaction. So in chemistry, we're going to track that change in energy during the course of a reaction, right, by looking at the enthalpy. It's going to basically tell us what's the heat absorbed or developed by a reaction. It's going to depend on the conditions under which that reaction occurs, but essentially that enthalpy is a measure of the change in total energy of our system. And it's going to be based on the energy of the reactants and products. And it's going to depend on the change in enthalpy during the course of a reaction will depend on the bonds that we're breaking and forming during the course of that reaction. So change in enthalpy for a reaction will be different for each reaction we look at because it'll depend on in that reaction, how many moles do I have, how many bonds am I breaking, and what are the bonds that I'm forming. But the important thing is that enthalpy is a state function. And I'll define a state function on the next slide. An example of a state function is change in height or a change in elevation. So a state function is important to understand because it does not matter the process, it just matters the difference from start to end. So what that means is it doesn't matter, right, how many steps I took to get from the start to the finish. It just mattered what was the change during that course of time. And so an example that you're familiar with of a state function is height or elevation. You could climb up the side of this mountain from your base camp all the way up to Camp B. You could go straight up the side of the mountain. Or you could take this meandering path to the same place. At the end of the day, your change in elevation is the same. It's the difference in elevation between Camp B and Camp A. So for example, if you are on the Empire State Building and you start at the ground floor and want to go all the way to the top, you could take the stairs or you could take the elevator. At the end of the day, you're going to have a same change in elevation. One of them is going to be a lot easier than the other one, but at the end of the day, the process that you're going through, the change in elevation, is the same. So it only matters where you start and where you finish. It doesn't matter the process that takes to go from start to the finish. The same thing is with enthalpy. All that matters is the energy that we start with and the energy that we end with. It doesn't matter if the reaction takes place in one big step or 10 little steps. All that matters is where did we start in energy and where did I end in energy for a reaction. Here's an example of that with respect to heat and work, right? Heat and work are not state functions. The total change in energy is. I could take two identical batteries that contain the same amount of energy. I could hook up one battery to a coil and just run that entire battery through the coil, producing heat and nothing else. So I have a change in energy only due to heat lost. I could also take that same identical battery with the same amount of energy and I could hook it up to a fan. The fan is going to move the propellers, moving the air. That's going to perform work, so it's going to lose energy through work. It'll also generate heat as well. At the end of the day, the change in energy from those batteries is the same. The amount of heat and work produced differs. And that's because heat and work depend on the path. And we're going to track that as the change in enthalpy during the course of the reaction. Basically, how much heat absorbed or released during the course of a chemical reaction. And because it's a state function, we can determine the change in enthalpy by simply looking at what's the enthalpy of the reactants and the enthalpy of the products and finding the difference between those two. So the change in enthalpy during the course of the reaction is equal to the enthalpy of the products minus the enthalpy of the reactants. And that's what we saw with the reaction coordinate diagram earlier. If here's the energy of my starting material, of my reactants, I go through that reaction, I absorb some energy. Here's the energy of my products. My change, right? This would be my change in energy during the course of that reaction. That would be my change in enthalpy during the course of that reaction. So here's an example of that. I could look at the combustion reaction of hydrogen and oxygen producing water. So I could calculate what's the energy of hydrogen and oxygen, what's the energy of water, and I could find that difference between the two to see that this is an exothermic reaction. This is going to result in the release of heat to the surroundings. So that change in enthalpy would be negative for an exothermic reaction. And that's what we see here. If I go and measure that change, I see that I've released 572 kilojoules of energy to the surroundings during the course of that reaction. So because this is a state function, right, only matters where I start and where I finish, this reaction also tells us a little bit more information. This also tells us for the reverse reaction as well. So if you started at the first floor and went to the 10th floor, right, you went up in elevation. Well, if you went from the 10th floor to the first floor, you went down in elevation. So if we reversed the reaction, for example, if I had two waters breaking down to give me two hydrogens and oxygen, well, then I would just change the sign on that enthalpy. That reaction would have to absorb 572 kilojoules of energy. So when we have these thermochemical equations, the equations that relate the enthalpy of a reaction, the heat of the reaction, to that reaction, they tell us not only the energy for the reaction as written, but they tell us for the reverse reaction as well. Because instead of releasing energy, as we do in the first reaction, well, to send the reaction in the opposite direction, we'd have to absorb energy. So the important things from today's lecture, you should be able to understand energy transfer through work, through heat, what it means for a reaction to be exothermic and endothermic, understand what a state function is, and we're going to look at these calculations in lecture on Wednesday.